Hello, everyone. So today I'm presenting my work on CyclOps for the past 8 months. Just as a bit of a disclaimer, this isn't going over CyclOps, the framework itself, specifically my work, so I hope you have some sort of knowledge of it, but we'll get going. So as a very high overview, it's a continuous evaluation framework for ML and health. So that essentially means going straight from end-to-end querying, processing, doing things like visualization, and then eventually we'll build out the MLOps type deal. So I'll start with kind of my first task. So that was on the querying. So we use SQL Alchemy's ORM to essentially get rid of the raw SQL strings that people, researchers, everyone generally deals with. So it's kind of to help extend things. It's to help reduce the amount of data queried. It gives a lot of flexibility to sort of provide that processing, and it just really sort of brings the pipeline end to end. So it kind of starts off with a low level where we have some functions to essentially handle like finicky SQL Alchemy quirks. So these are things like doing certain checks, gets, transform conditions. You can kind of see an example of an assert and a transformation there at the bottom. On the high level, we essentially abstracted away SQL Alchemy entirely. So if we ever switch it out, that kind of high level modules will still work. But you can see here there are certain things like dropping columns or joining two tables, ordering, trimming, things like that. And then here you can just see one example of creating this module, essentially putting in some parameters, and then inserting the table at the end to perform that transformation. Then we get to the database level. So this is essentially database-specific sort of querying that we've created for Gemini and Mimic 4. And you can see that it's essentially doing things like, typecasting. We get some sort of disposition code descriptions, joining. There's also some sort of optional operations that users can provide, such that they don't have to implement that functionality themselves. And then you can see here, that's kind of what the user would see if they wanted to sort of query from this, which brings us to the user level. Basically, the same sort of idea, but now if you were going through a whole use case, this is what it might look like when you're querying from the different tables. So we see we're getting sort of patient encounters from certain years. We have events and imaging and so on. At the bottom, you can see on the left, you can see we're running it using our interface. So it essentially makes it super easy to run these queries. You can limit them, things like that. You can also sort of take the queries out of the interface, you see on the right at the top there, and provide your own transformations if you'd like. There's also some sort of preliminary work on sort of query batching using sort of file saving and generators. So that's super nice when it's impossible to sort of load up an entire query memory at once. Then we get onto the processing. So this is essentially generally the first step in the processor is to featurize. So that's essentially parsing the raw data frame into something a bit more manageable. So this is kind of what we call our features objects for sort of arbitrary data frames, or our tabular or temporal for sort of more specific data types. It does things like record feature metadata, so like whether it's a feature, target, or something else. It has things like ordinal variable mappings, a couple other things, and then it also, I think the most useful bit of it is to essentially detect and handle feature encodings. So if it sees some strings, doesn't have too many unique values, then it can kind of assume that it's categorical and make the necessary transformations. Then we move on to aggregation. So this is for sort of temporal data and modeling. You can kind of select different groups over which to aggregate and then provide custom or even predefined sort of aggregation functions to use. And you can see an example of that on the right, where we're essentially doing some mean aggregation. We provide the timestamp column, how we want to group, and then some things like time, step size, window duration, define the features, and then we essentially just call .aggregate, which is again sort of specific to temporal features, which is why you might want these kind of objects to be specific. Now we have the vectorization portion. So this is where we essentially want to vectorize either the tabular features or aggregated data. So it's essentially just converting from a data frame into an array. This is super simple for something like tabular features where it's just two-dimensional. You basically just do df.values. But it's a lot more challenging for sort of aggregated data. And you have to kind of do a bunch of group bys, indexing, sorting, just to kind of get it to make sense. So here you can just see like a mini code snippet there with the .vectorize. And it actually turned out that the aggregation and vectorization of temporal data specifically was like extremely time intensive. It was essentially slowing down our entire pipeline. So some pretty serious focus was given to improving that efficiency, and we did that pretty well. Once it is vectorized, we realize that kind of most sort of users, people in ML, they lose track of the features. They don't really know where things are. Essentially, the second you vectorize, you're kind of done. That's your final data. And we really didn't like that. So we essentially created this vectorized object that will track which axis is where in your array, and then also within that axis, what do the different indices mean? So let's say indice 37 corresponds to feature A or event A. By keeping track of those things, it allows you to do a lot of different operations, which are previously impossible. So this is things like taking a feature subset or removing certain features, as well as just doing something like a target feature split. So this isn't all of these sort of operations. There's a lot more, but it's just kind of what we could show in this short presentation. Then comes the imputation. So this is kind of supported within the vectorized objects where you compute over an axis. So there's kind of a very simple one here where we can essentially fill the time steps forward for some temporal data and then fill backwards to make sure they're all nice and filled. There is a couple imputation functions just implemented already. So like mean, median, sort of like value filling. And then same thing with like the fill forward, fill backwards. But any function can actually be passed in for total customizability. And essentially, you give it the data with some missing values, and you send it back with them filled. Then we have the normalization, and there's actually two objects which can perform this. There's the group by normalizer, which basically operates on data frames or the features objects, and then the vectorized normalizer, which of course operates on the vectorized object. So they both work pretty similarly. The group by basically groups and then applies the normalization function, whereas the normalized or the vectorized normalizer sort of does it over an axis, same kind of way as the imputation. So you can kind of see here on the left that we are normalizing all features for this tabular data, and you essentially just put in the normalization method, or you can actually specifically specify things within the axis to normalize. So here we're only normalizing numeric features on the right. So that's kind of some nice flexibility. And then we have the dataset split. So this is essentially, again, you can use data frames or vectorized. We kind of show the vectorized here because it's kind of the more built out capability. But essentially, you can use the subset fractions to split a data set. So here we have some sort of tabular vectorized. We put in an 80-10-10 split. So that's giving us our train, validation, and testing. Or you can even split multiple data sets together. So this is especially useful for if you have something working with multimodal data and you want to keep everything along the same axis. So it's essentially like if there's encounter 100 in one, it should be in the same axis in the other data set, right? So that's kind of what it's doing there. And you can see like the 15142 in each one kind of corresponds to that encounter ID or samples more generally. Finally, or not finally, we have the generalizable notebook pipeline. So this is essentially because with no current workflow and functionality in CyclOps, we needed something that was a bit more generalizable for our pipelines for our mortality risk prediction use cases, which we'll get to. So it kind of starts off with our querying, which is actually the only use case specific notebook, but it starts off with that. And essentially the output is a clean data frame with some features that are engineered in it. Then it moves on to the tabular processing, which essentially just outputs the vectorized tabular features, does a bit of cleaning, things like that. And then all process essentially does the temporal data, but it actually aligns the vectorized tabular, temporal, and then combined, which is essentially where we turn the tabular into sort of a temporal format and then combine that together such that you can sort of have both tabular and temporal in one object. Then we have the tabular modeling, which is with our XGBoost, which is very simple, and our temporal modeling, which is with our RNN type models, like we use an LSTM. So now we actually get onto the use cases themselves. So it's essentially in-hospital mortality risk prediction across two use cases with two different data sets. So both of them are utilizing that notebook pipeline, but essentially one of them is for the internal vector research. So essentially this is research that Amrit and Vali were doing originally on Gemini that I essentially extended to the Mimic4 data set and also updated to use that pipeline. Then there's the Wong Lab research, which is essentially something they already had working on Gemini, but we then adapted it to CyclOps, introduced temporal modeling, which they didn't have before, and we essentially improved the end-to-end processing time, including querying from like hours into minutes, which is solid. Then there's a bit of like processing wins I wanted to mention, which is that I essentially came up with a nice sort of generalizable label creation for like single event temporal modeling, so like death, for example, got that sort of working well, and then also some custom sort of loss reweighting. So it's a very time and space efficient strategy for sort of mitigating issues of data imbalance, because we were kind of looking at outcome rates of 5% or less, as low as 1%. So we essentially did that loss reweighting, and it sort of represented some serious gains in terms of performance. So here we actually see a bit of results. So this is for the temporal results with the LSTM. So essentially the problem definition is, for the first 6 days of the patient's encounter, predict every 24 hours whether a patient will die within the next 2 weeks. So same problem definition for both use cases, different initial data used though. So here we can see for the vector, we got an AUROC of about 8.5 or 0.85. And then for the Wong lab, we got an AUROC of 0.87. So I think these are quite good results, especially since they're kind of initial. So these are kind of recent, and I'm sure that we will keep improving them as we go in the future. Then we have essentially the non-technical interface, and I do actually have the demo up for this, but depending on time, we'll see if that's available at the end. But essentially, this is the beginning of an interface built with Dash, and the whole point is that it's supposed to be making CyclOps accessible to sort of clinicians and other non-technical users. So it would be for things like querying or cohort curation, data processing, and EDA. So even potentially mixing in all the different tools for, or sort of visualization for CyclOps that we're planning could potentially go here. And yeah, so I think that is pretty much my presentation. Here you just kind of see some fun CyclOps logos that we're brainstorming or AI generated. But yeah, I thank you a lot. I don't know if I have time for like a mini demo or not. I have 2 minutes. That includes questions. Okay, why don't you guys throw questions at me and I'll just like bring this up if anyone has any. Like if you have them, please ask now. I'm just going to show this as it's happening. Yep. Yep.
Depending on what that was.
Yeah. So it was pretty much just, so essentially for our losses here, we had essentially 0 for when the patient is alive, right? So it's essentially a 24-hour offset, or sorry, 2-week offset for, you know, predicting 2 weeks in advance, obviously. But if the patient was alive, it was 0. If they were dead, it was 1. And if they were discharged, then it was -1. And so essentially, we had to do some custom reloss weighting to deal with those -1s to essentially say we took the total sum of sort of 1s divided by the 0s to get like a factor of about 15. So we're essentially saying when the patient actually is dead, when the label is 1, treat that loss much more significantly than when they're still alive. So that kind of allowed us, with such a small outcome rate, to actually make a difference in terms of that. Hopefully that makes sense. Okay.
Doing what did you say about the most challenging?
The most challenging, is that in terms of technically or?
I was thinking technically.
Okay. The most challenging, honestly, was really the design, to be honest, because we're building something that is truly massive. We're even going to, like, we're planning to modularize it and things like that, such that we're kind of basically creating several sort of components or repositories. So that's still in the works, obviously, but yeah, I think it was just designing it such that it was extremely general, extensible, really just taking those design principles into account with every single step. Yeah, I think that was kind of the most challenging is deciding, you know, what to do and when. But yeah, that is my presentation. Thank you very much.